Hello everybody. In this video, I'm going to discuss classification of organic compounds. So let me write it. Classification of organic compounds. When you're studying organic chemistry, normally you study about the carbon atoms first, which should be an introduction, which will include hybridization, understanding of that, molecular orbital theory, and then my suggestion is to understand the classification. So that's why this video is about classification of organic compounds. What you need to be able to do after watching this video is to identify different functional groups. Let me use different functional groups. Classify. So you identify the functional group, then you should be able to classify according to the functional groups. And you should be able to identify the formula and structure according to the functional groups. We are not going to detail that. Mainly, I'm going to classify, and then there's a calculate the degree of unsaturation. I'll give you the formula to calculate. I'm not going to elaborate on that part. So when you draw, we'll say a simple compound. You can draw, we'll say methane. You can draw the compound or give the information about the compound by writing molecular formula. It will be CH4. What does it tell? It tells us there's one carbon atom and 4 hydrogens. It doesn't tell the arrangement. It doesn't tell about the chemical. So this is a molecular formula you can use. Then you can also do a structural formula. Because before I classify, I want to tell you the different ways of writing. So in the classified formula, we can have a displayed formula. So molecular formula, structural formula, we have displayed formula. When it comes to methane, it would be so this carbon is the central atom, hydrogens are peripheral atoms. If you know the Lewis structures, how to do them, this is what you get. So you have to understand is when you draw something, I'm going to display this formula in a 3 dimensions. So first I showed you just on the plane. So if I'm going to do it in 3-dimensional form, so this is the plane of the paper or the iPad I'm using. A straight line means on the plane of the paper. Okay. Then if you have a broken line like that, or do it that, I will draw this methane molecule accordingly after that. That means it goes into the paper. in a three-dimensional setting into the paper. It's going below the plane of the paper. If you do a bold line like that, what means it is coming out of the paper, out of the plane. This is the paper, out of the paper. Okay. Now, when we draw this one following this three-dimensional form, I'll have one hydrogen like that, plane of the paper. One is coming out of the paper, and one is going below the. Right, so these are the different ways. So normally we don't go into details unless we are asked, and then draw the angle, and yeah, we just stick to this normal, easy way of displaying the formula. Another way is skeletal formula. Third formula. Skeletal formula. That is the points or the ends. So the point or an end of a line, we consider it as carbon. So an example, if I want to write CH3, CH2, CH3. Now what is this one? This is a displayed. But out of this, if I'm going to do a skeletal, I will draw like this. That's it. So that is it. That is the skeletal form of that. What it means is carbon, carbon, carbon. We assume from our knowledge, we know if it is N carbon, there should be 3 hydrogens. If it is in the middle carbon, no double bonds or triple bonds, there need to be 2 hydrogens. And they should have 3 hydrogens. That's it. So this is a skeleton. Okay. Now, when you draw long structures, sometimes they use skeletal formulas, but if you do the displayed one, it is clear. And even the skeletal ones, we can write, if you have a double bond, triple bond, you can do like this, like that. That's showing the double bond. Okay, it's a different compound. So if I do the displayed formula for that, it would be, I'm writing this hydrogen on the other side just to show that carbon is connected to the carbon. There should be only 1 hydrogen because there's double bond. So total number of bonds a carbon could have is 4. So hydrogen, 2 hydrogens going here. Okay, sorry, this is going. I have another carbon here. I write that. So here also another hydrogen, and then that's the displayed formula from the skeletal formula. Okay, now that we know what they are, let us talk about the classification. You need to understand certain terms. If you say cyclic, means carbon or organic compounds forming any shape of cyclic ring forms. Okay, cyclic. If you say acyclic, then there are no rings, there are always chains. They could be branched or non-branched, but they're chains, so direct. Carbon, maybe, but they are not making any rings, no rings. Then if I say alicyclic, alicyclic, they form rings, and they also might have some aliphatic group attached to that, because acyclic means no cycle, so they use sometimes, mostly use aliphatic term. So it's acyclic, it's aliphatic, so that they may be chains or branches. Alicyclics are like, for an example, let me see if I have a compound C6H14. I will draw the molecular formula. Displayed one, 1, 2, 3, 4, 6. It's hydrogen, hydrogen, hydrogen. Because this is a saturated one, aliphatic. So that's an aliphatic. In alicyclic, these combine to give a ring. So alicyclic, a cyclic form. So if I just combine this carbon at the end to the other carbon, I remove these two hydrogens, and then I can make a cycle like that. Six. And then I have two hydrogens here, two hydrogen bonds here. Hydrogen atoms. So this formula is going to be C6H12. We have lost two hydrogens because these two corners hydrogens were taken off. This is an alicyclic compound. Yeah, these compounds could also have another long chain attached to them, but they are called alicyclic. So hydrocarbons, which in only hydrogen, carbon, hydrocarbons, we can categorize like aliphatic. This one is non-cyclic, acyclic, okay, and alicyclic. There, what is alicyclic? The one we drew here, just combining. Then we have aromatic. Now, in an aromatic one, there is a conjugation, which is alternative double bonds. So it could have aromatic ring or double or triple bonds. Okay. So this, to find this aromatic nature, there are some calculations. Towards the end, I will just mention that. So what is aromatic? Classic example is benzene. Now you can see C6H12 is cyclohexane. If we go for the name, this is just hexane. In cyclohexanes, only it is two hydrogens less because it became a cycle. And in benzene, it is C6H6, and it's drawn like that. I'm showing the skeletal formula. You can see these double bonds change. Okay. So hydrocarbons could be classified as aliphatic, which is non-cyclic or acyclic, alicyclic, which is this part here, alicyclic, or aromatic. Aromatic is like benzene. The reason I put this double arrow is because this benzene could have two resonance structures, because those double bonds here could change and it could get to these places. Okay, so generally, because those double bonds move around, signify it like this with a ring inside benzene circle. All right. So let us clear this again and say the classification. Hydrocarbons, aliphatic, I explained them now, aliphatic, alicyclic, and aromatic. Heterocyclic compounds are there. Hydrocarbons has only carbon and hydrogen. When it comes to heterocyclics, right? In heterocyclics, there are cycles and one or more carbon atoms have been replaced with a heteroatom, an atom other than carbon. Okay. Then we have compounds. Hetero atom functional groups. Okay, so those are the three classes. Heteroatom functional groups. What are the heteroatoms other than carbon? Other than carbon, it could be nitrogen, it could be oxygen, it could be sulfur, things like that. Those are the heteroatoms we are talking about. Okay. So when it comes to aliphatic hydrocarbons, as we know, we have only carbon and hydrogen here. So carbon could have only 4 bonds unless there are more than single bond. So maybe a double bond or triple bond between two carbon atoms, then it would have fewer hydrogens than that it would require if it was a single bond. Okay, so the formation of either carbon single bond or double bond or triple bond, it's coming, you can understand, through hybridization. Okay, so let's go for these groups. There are 3 types: alkanes. This is saturated. Now in study organic chemistry, you have to study these different classes separately. So I'm just giving general example. Okay, saturated, all are single bonds. They follow the CnH2n plus 2. Right. Now, if it is not single bond, then we have alkenes. Now, these alkanes, all these things, they also form, the arrangement could be different. Now, alkanes, we'll say, if you take butane, that is coming under naming of compounds. So that is a separate video. Just accept this name, what I'm telling you now, and go by that. So butane, which is so if no single, all are single bonds, no unsaturation. So I can draw like this. This also could be drawn like this. Right? Same number of carbon atoms. Same number of hydrogen atoms. So 1, 2, 3, 4, 8, and 10. It's 10 here. If you use this formula, C4, H becomes 2 times 4 plus 2. It's 10. This is an isomer. The previous one. Okay. Now these things we will discuss when you do the nomenclature. I just wanted to just to introduce you to that concept, isomers, and how they look the same, how the number of atoms in both formulas are the same, but the displayed formula are different. So alkenes, double bonds. That is the unsaturation. Okay, they are not saturated because you could, if you draw something like that, and then it could have hydrogen. You can add more hydrogen and make it a single bond. This one, right? That is one. Now, for the formula of that one, it will be CnH2n. Similar to that, we have alkynes, which has triple bonds. Now here it can have only one hydrogen. It means each carbon could have only one hydrogen. So the formula is CnH2n-2. These things you will learn in detail when you study about these compounds separately. Okay. Now let us talk about alicyclic compounds. I have explained what is alicyclic compound. We'll say it is a combination of aliphatic hydrocarbons together. So if I showed you cyclohexane before, cyclohexane. There's no, if there's no unsaturation, it should be 2 hydrogen atoms in each carbon atom. One. Now you can see the root name. These things we will analyze further when we study about the naming of compounds. Pentane, but it's cyclo, so should be able to intuitively assume that there must have been a pentane ring that has made the combination and ends up being a cyclopentane, an alicyclic compound. These are different to aromatic compounds. Remember that. That's a separate special class. This one. So one example is benzene. This is the skeletal. It is displayed formula. 6 carbons, but there are double bonds alternatively. So it will have only one hydrogen atom in each carbon atom. Molecular formula is C6H6. I told you about the resonance. Now this aromaticity has been observed in other conjugated cyclic systems, ene or polyene system. You can see this is ene. Okay, so this is where the naming of compounds we talk about. We said alkene. Ene means double bond, refers to a double bond. So these are double bonds, but it's cyclic and there are more than one double bond. So I will call it polyene. Okay. So this aromatic nature or aromaticity is observed in other compounds too when they have this alternating conjugated bond. So there's a calculation to tell how many pi electrons are there. Like benzene has 6 pi electrons. 1, 2, 3, 4, 6. So this rule to calculate was given by Huckel. And that is given as for a planar molecule, on the plane like this, on the plane of the paper. 4n plus 2 pi electrons. This formula determines aromaticity of a closed shell, N is what is N? N equals the number of closed conjugated polyene shells. It has to be closed, conjugated, polyene shells. In benzene, there's only one closed one. There's only one, so N becomes 1. Then number is 6 pi electrons. Let's take another one. Rule is so I'm just going to do something. Okay. This is called naphthalene. Let us apply this formula here. N, these two rings are fused together and they are closed. They are polyenes and they have conjugation. Right, so here these double bonds are alternating. That means conjugation. Okay, so N is 2 here. So I have 4 times 2 plus 2. I have 10 pi electrons. It's okay to use the formula when you're looking at it, but the idea is if you are given the number of closed cells, you can just automatically say how many pi electrons. I'm not going to go into extreme calculations of other compounds like aniline and things. This is if you're going to study organic chemistry and major in that, then these things will be important. What I'm trying to do is give you a general idea about the classification of compounds. All right. Now let us do heterocyclic compounds. I said heterocyclic compounds it's a cycle made out of carbons, but one of the carbons, one or more carbons, replaced by some other atom other than carbon. That's why the heteroatom. Okay, so these are the examples. This is a compound that is replaced by nitrogen. This is called pyridine. reason is so that you know that what it means by heterocyclic compounds. You might not deal with it depending on the level of study you do, but this just to understand, for you to understand. Okay. That is furan, pyridine, purine, pyrimidine, pyridine. These things you should know if you have done your biology, DNA molecules, and things like that. Okay. All right. So we talked about heterocyclic compounds just to give an idea how it comes. We talked about aliphatic and alicyclic. I'll just go through some of the functional groups now. Okay. Now, the heterocyclic compound, just want to mention here. So once I talk to you about different functional groups, the heterocyclic compound could be attached to those functional groups, or the functional group could be attached to those heterocyclic. So that's a separate thing, but we'll say just so this is a functional group, carboxylic acid. Okay. The reason you need to know this functional group is because when you name the compound, there's a priority order. So you use that one to name the compounds. Now, you would not know the priority order if you don't know about the functional groups. That's why I'm with this one, carboxylic acid. Now, this carboxylic acid could be attached to that pyridine I told you earlier. So when this is a heterocyclic, because nitrogen there, this pass is hetero. Cyclic carboxylic acid. So the name heterocyclic carboxylic. What is it? What is that? If then you get the name and then attach to that. Okay. Now, if something like that is a benzene, then, so this is aromatic part, aromatic carboxylic acid. Right? Likewise, so we are not going to detail into that. So I'm avoiding naming the compound. So that's how we do it. Okay. There is a, if you go into advanced studies, there is a range where you can further classify aromatic, anti-aromatic, and non-aromatic compounds. Aromatic, anti-aromatic, and non-aromatic compounds. If something is not cyclic, planar, and conjugated. If something is not any of these things, they are called non-aromatic. Okay, it's like half open cycle. So if I draw something like this, okay, this is a skeletal diagram. Yeah, draw like this. See, it is not cyclic. It is a planar, but conjugated. They are okay, but it's not cyclic. So as a result, this is non-aromatic. But if they fall into this category, and if they have 4n plus 2 pi electrons, when you calculate the number of conjugated electrons, and it matches this rule, Huckel's rule, then they are aromatic. Benzene. But if they don't fall into that category and it has only 4 pi electrons, then they are anti-aromatic. That's how the calcium comes. Depending on the level of study you are doing, this may not be important, but just understand cyclic, planar, conjugated, if they don't match any of the things, not all three does any of the things, non-aromatic. All three matching, then if you had 4n plus 2 pi electrons when you count separately, then they're aromatic. If they have only 4 pi electrons, they become anti-aromatic. Now we are going to talk about we talked about 3 types, so this is the 3rd type, compounds with heteroatom functional groups. So first understand the carbonyl group. So the functional group where carbonyl groups become the functional group in this one. Okay. Now, before I tell that, this is a very important group. I'll go try to make it systematically. If there is one bond between heteroatom, I'll put okay, between the heteroatom and the carbon, then that is a different functional group. Example, alcohol. The functional group is written as C, so OH. Can you see this? This is the heteroatom, and there's one bond. Alcohol, ether, like this. When you study each groups, alkanes, if you have an alkane which has CnH2n plus 2 formula, which is, we'll say, CH4, but if you take one hydrogen, you end up with a group called alkyl group. Okay, minus H, then I will get CH3. Likewise, in each alkane, if we take about alkane or in the group, take about one hydrogen and then connects it to the rest of the carbon that is connected to that, we can put R. We can denote it by the letter R. So this side also R. Okay, so ether is generally drawn like this to show it, or alcohol is written like ROH. We have to assume that there's a long carbon chain and the nearest carbon is attached to OH group. So alcohol functional group is OH. It's combined with single bond. In ether, it is O. Right, it's combined to one of the R groups. That's ether. Okay. Then the other one is there are nitro groups attached like that. We say nitro. Okay. So that is one bond between the heteroatom and the carbon. Then, depending on the situation, you will learn more about this tertiary, primary, secondary forms of these alcohols and ether and things like that later. Okay, so let me do this one. Another group is, because we are talking about alcohols now, thioalcohols. That means you have a SH group. Instead of oxygen, we have put S. Then we call thioalcohols, TH. Thioalcohols or thiols. Thioalcohol, it's easier because OH is alcohol. This is S-thio, so you call it thiols. Always whenever OL is there, you know it's OH there, but it's thiol coming, you know that is SH is connected. So it's RSH. Thioalcohols or thiols. Alcohol groups. Another one is phenol. Benzene attached. This is then, so alcohol, you know that if it is directly right here, the carbon okay. Alcohol, I have SH, that is thiol. If I have a benzene ring attached and OH, that's phenol. Then ether, if you have just oxygen right here, but if this oxygen is replaced as by sulfur, then same as thiols, thioalcohols, thiol, this is become thioether. Sulfite. Another heteroatom that could connect would be if any halogen, I'll put X is anything like chlorine, fluorine, bromine. So if you have F, that you call it, F means fluorine, then you call fluorocompounds. If you have bromine, you call bromo. If you have chlorine, you call chloro. Okay. So if it is iodine, iodine. They also could have primary, secondary structures, but it depends on the situation. Here now, this is part I'm just telling you different function groups. That's what I'm doing. Okay. Then another function group is amines. This is a function group where carbon has only one bond between them. That's what it do. So it's amines if you have nitrogen. So I will show like this R group. There could be one hydrogens, two hydrogens, right? These could be changing, and depending on that, you call primary or secondary. Here at this, in this video, you just have to see different functional groups, and that's all. You don't have to go for primary, secondary. That part you do when you do the naming of compounds. So this could be that is amine. Primary, secondary, or tertiary. Then you have phosphine. See, that is if you have phosphorus, phosphine part. When nitrogen atom you replace, you get phosphine. Then you have nitro. About NO2. So you have R group there. You have R group there. Okay. So that is one bond between carbon and the hetero atom. Lights. Thioether. Alcohol or thiol. Phosphorus phosphine group. phenol. If this carbon is let's see, phenol, right? And amine. All right, so these are the functional groups that, because I'm classifying these according to the bond between carbon and the heteroatom. So when it is a single bond. Now let us go for it. There are two bonds between the carbon and the heteroatom. Okay. First example is aldehyde. So I told you about the carbonyl group. That's where we bring in carbonyl group here. R, C. Now that is an aldehyde. Okay. Carbonyl group is there because it's a double bond. That's why it comes under this category. Then the next one is ketones. Instead of hydrogen here, we have R group. Then we have imines. Ketone. Imines. Imines has structure. Double bond between the carbon and the nitrogen. That is imines. Okay. I don't have space here, so let me clear. Now we'll go for when it has three bonds between the heteroatom. So example, cyanide. Carbon and nitrogen, that. So this is our continuation. These are the cyanide. Okay. Then what if carbon has two heteroatoms? So three. So the three atoms, I need only the cyanide, which is the cyano group attaching here. That's the example I can give you here. Let us see now if we had two heteroatoms. All this time we talked about only one. So example is carboxylic acid. So you can see there's a heteroatom. We don't count hydrogen as a heteroatom, so that group. Okay, these are carboxylic acid, and any derivative of that. So carboxylic generally written as RCOOH. It's the same as the above one. The molecule formula, displayed formula there on top. Okay, so two heteroatoms, carboxylic group, and the derivatives. So let me draw the derivatives. So you might wonder, I might have to remember all. Yes, when you keep on doing these questions, you will remember, but this is the easiest way to remember by understanding single bond, double bond. The classification I have given is here is the easiest way to remember. Okay. Then acid halide. Acid halide. When you say acid, you have to think that it must be a derivation of carboxylic acid. So carboxylic acid like this. Instead of OH, we have X acid halide. See that? Then ester. Ester is, instead of OH, we get OR here. Okay. Now, in inorganic chemistry, you study acid and a base always give salt and water. Ester, you can remember always carboxylic acid, and alcohol gives ester and water. Okay. So, then acid and hydride. Acid and hydride. That is, you have RCOOH O. This pen is not writing. Let's see what. Okay, acid double O, and then it is connected with O and another one on the other side. These R groups don't have to be the same. Okay, acetone. This is anhydride. So the water molecule leaves two carboxylic acids coming together. Water molecule goes away. Then this connect. Clearer. So OH. This has. So this H2O goes away. Then to combine. Acid anhydride. Then amide, where RCO and RO join when nitrogen joins here. So earlier, if we had a carbon just in RONH, there's an amine, right? When this carbonyl group is joined by that amine, then you can say amide. Once again, if this is a tertiary, then there could be secondary, then it could be primary. Okay. We also get sulfonic acid. Sulfonic acids and derivatives. That is SO. So the entire thing, now it's not a carboxylic acid, it's a sulfonic acid. Then sulfonic acid also could undergo, it is joined by a chloride or a ester, all the things, the same thing, but with sulfonic. Unless you're doing majoring in chemistry or something, you will not be coming across these ones very much. This is sulfonide chloride. Okay, I bet sulfonic, you know. Okay. Right. Similarly, you have sulfur. Always this SO group stays and whatever the other parties take it, all right? So you have, I'll put O. It's an alcohol, right? Ester is given by carboxylic acid and an ester. So it's a sulfonate ester. It will be sulfonic acid and alcohol, sulfonate ester. Then we get sulfonamide. State that one. Just replacing carboxylic acid with sulfonic acid. That's it. Then there are further ones. That 4 bonds between heteroatom and carbon. Okay, I will just give you one example. So if you have 4 bonds between carbon and the heteroatom, when you make 4 bonds, not at once, carbon can't make it, but from both sides. Okay, so I'll just give you one example so that you have heard it, seen it here. Urethane. Take urethane. O. So here 2 bonds. 1 bond with oxygen, another one is nitrogen. So all together, surrounded. All 4 bonds are separate ones. Another example, if you get Rn, 4 bonds. It's isocyanate. So my purpose was to show you different functional groups and to recognize them. You will be coming across only a limited number of ones. Like for an example, very rare you will go for these 4 bonds between carbon and the hydrocarbon atoms. I just want to show you the formula for the degree of unsaturation. You know, the unsaturation is double or triple bonds happening. Saturation is calculated by this equation. Degree of unsaturation, DOU, plus 2 carbon plus 2 plus. So N is the number of nitrogen atoms, X is the number of halides, you know them by that. This is halides. Okay. This number of N's, nitrogen. C means carbon atoms. And H means hydrogen atoms. Okay. Now oxygen and other divalent atoms, they don't contribute. So oxygen is not taking, or any other divalent atoms. So we don't take them in this calculating as the saturation, unsaturation. All right, everybody. So this is just for you to remember, and that's all I have to say about the classification. If you watch this again, it will become easier and easier. Then you know that mostly you stick to aliphatic or aromatic. Alicyclic, yes, when you're studying about aliphatic, you choose to go on to alicyclic compounds, but then aromatic, they are the ones that would dominate when it comes to the functional groups. Carboxylic acids, alcohol, esters, aldehydes, ketones. They're the ones you come across. Amides. Amides and hydrides and acid halides. Okay. Those are the ones. Other ones, just for your knowledge, expand. So when you come across those ones, you can come back to here, say, oh, this is the classification and it falls onto this category. Thank you, everybody. I hope you gain some knowledge.